atomic bomb. How great! Weighing in at 9,700 pounds, we have a little boy in the right corner. And in the not so right corner, we have Fat Man weighing in at 10,300 pounds. Win this fight, it's gonna take an atomic bomb, baby. Yeah. The first thing that happens is this fat guy farts, and we all die. Yeah, it's pretty nice. If I do say so myself, man, it's just pure folly, man. I love it, man. I just love it. Yeah, can't let it go.
You know, great track that.
Oh, mate, love it. Quality.
Listen.
Pure quality, bruv.
Bruv, what's your name again?
What? What's up, son?
What's your name?
Lee, what's up, son?
No, not you.
This is just a short video on an explanation of how atomic bombs work and how the atoms get split in them. I will not be giving full details on exactly how they work, I'm only explaining it in a nutshell.
First off, atomic bombs either use one of the two materials, uranium-235, which was used in Little Boy, or plutonium-239, which was used in Fat Man. The reason why they only used the two materials out of 118 elements is because they are unstable isotope. Uranium and plutonium have unstable isotopes, which means that the plutonium and uranium atom have much more neutrons in the element into more stable, smaller elements. This makes the two elements radioactive. There are different types of plutonium and uranium, but they only use uranium-235 and plutonium-239. So now that we know why they only use plutonium and uranium in atomic bombs, now we need to know how the bomb is set out and how the atoms get split.
A neutron is fired at the nucleus.
The nucleus becomes uneven with neutrons and protons.
To balance itself, it splits into two.
This process is called nuclear fission. Nuclear fission was used in Little Boy and Fat Man bombs. Put it all together, and here's what you get. Two types of atomic bomb were developed during the war. A relatively simple gun-type fission weapon was made using uranium-235, an isotope that makes up only 0.7% of uranium. Fission. Da da da
In this video,
da
we're going to talk about
da da.
fission. Unstable radioactive nuclei.
When a nucleus fissions, it splits into several smaller fragments. These fragments, or fission products, are about equal to half the original mass. 2 or 3 neutrons are also emitted. The sum of the masses of these fragments is less than the original mass. The missing mass, about 0.1% of the original mass, has been converted into energy according to Einstein's equation. Fission can occur when a nucleus of heavy atom captures a neutron, or it can happen spontaneously.
A million times the energy of the neutron which triggered it. He, along with his two colleagues, Lisa Meitner and Fritz Strassmann, found that when the nucleus of uranium-235 is bombarded with neutrons, it will absorb one of the neutrons. This results in an unstable compound nucleus, and the nucleus breaks into two equal parts. This process is referred to as nuclear fission. So, a process in which heavy nuclei are bombarded with neutrons and split into two equal masses, releasing enormous amounts of energy, is called nuclear fission. In the process, uranium-235 initially absorbs a slow-moving neutron, thus forming a highly unstable compound nucleus, uranium-236. This is what triggers the nuclear reaction. During the process of fission, uranium-236 splits into two product nuclei, which are barium-141 and krypton-92. You should notice that a barium atom has 56 protons and a krypton atom has 36 protons, which add up to the uranium atom's 92 protons. The unstable uranium-236 nucleus also releases 3 neutrons in the process. This happens because barium-141 has 141 neutrons and krypton-92 has 92 neutrons, adding up to a total of 233 neutrons. To balance the equation, uranium-236 must emit 3 more neutrons. The chemical equation of the nuclear fission reaction taking place can be represented by this equation. So as you can see from the equation, one neutron combines with uranium-235, forming an unstable compound nucleus, uranium-236. This unstable nucleus splits into 2 stable nuclei, barium-141 and krypton-92. In addition to these 2 nuclei, 3 neutrons are also emitted, as well as a high amount of energy, denoted in the equation by Q. Since uranium-236 emits 3 neutrons in the reaction, these neutrons can be absorbed by other uranium-235 nuclei, resulting in a chain reaction. This leads to exponentially high amounts of energy being released by a single reaction. So, in this video, we've covered that nuclear fission reactions result in massive amounts of energy being released. Now, these nuclear reactions are most well known for the part they play in nuclear bombs, but they are also an essential part of nuclear reactors, which have the capability to provide mass amounts of energy with relatively low cost. But that's a different topic altogether.
Nuclear energy can also be released by fusion of 2 elements with low atomic numbers. The power that fuels the sun and stars is nuclear fusion. In a hydrogen bomb, 2 isotopes of hydrogen, deuterium and tritium, are fused to form a nucleus of helium and neutron. This fusion releases 17.6 MeV of energy. Unlike nuclear fission, there is no limit on the amount of fusion that can occur.
So, nuclear fusion can simply be defined as the fusion or combination of nuclei. Scientifically, nuclear fusion can be defined as a nuclear reaction in which lighter nuclei are combined together to form heavier product nuclei with the release of enormous amounts of energy. For example, lighter nuclei such as lithium and helium, when combined together, form a heavier nucleus. The mass of the heavier nucleus is less than the initial reacting nuclei. The word heavier here is phrased in terms of energy release, which is usually very enormous rather than mass. Therefore, the law of conservation of energy is satisfied. Consider the example of 2 hydrogen nuclei combining to form deuterium. Here, one hydrogen atom combines with another hydrogen atom, giving deuterium, 1 positron, and 1 neutrino. This deuterium, in turn, combines with another hydrogen nucleus to form a helium isotope. If 2 such helium isotopes are fused together, the formation of heavier helium takes place. These three steps of a nuclear process, where 4 protons are fused together to form the heavier helium-4 nucleus and enormous amount of energy, is a nuclear fusion reaction. The chemical equation for this nuclear fusion is as follows. 4 hydrogen nuclei, when fused together, give rise to the heavier helium. But how is this enormous amount of energy being liberated from such a seemingly simple nuclear reaction? To understand this, let's first calculate the loss of mass in the process. The starting mass of the 4 protons is 4 times 1.0078, which is equal to 4.0312 AMU. But the final mass of a helium nucleus is 4.001506 AMU. Therefore, the loss of mass is 4.0312 minus 4.001506, which is equal to 0.0297 AMU. This is equivalent to the energy given by Q is equal to 0.0297 AMU times 900 mega electron volts per AMU, which is equal to 27.67 mega electron volts. Wow, that is a significant energy release coming from the fusion of the 4 protons. However, in spite of such a substantial amount of energy being released in a nuclear fusion reaction, there are no full-time nuclear reactors built so far for fusion reactions, as it is very hard to control such enormous energy release.
The initial death count in Hiroshima, set at 42,000 to 93,000, was based solely on the disposal of bodies, and was thus much too low. Later surveys covered body counts, missing persons, and neighborhood surveys during the first month after the bombing, yielding a more reliable estimate of 130,000 dead as of November of 1945. A similar survey by officials in Nagasaki set its death toll at 60,000 to 70,000. Its plutonium bomb was more powerful, but its destructive range was limited by surrounding hills and mountains. Additional counts indicated high levels of short-term mortality in both cities. Over 90% of persons within 500 meters, or 16,000 feet, of ground zero, where the bomb hit, in both cities died. At 1.5 kilometers, almost 1 mile, over 2/3 were casualties and 1/3 died. Of those at a distance of 2 kilometers, or 1.2 miles, half were casualties, 10% of whom died. Casualties dropped to 10% at distances over 4 kilometers, approximately 2.4 miles. Most persons close to ground zero who received high radiation dosages died immediately or during the first day. 1/3 of all fatalities occurred on the 4th day, or by the 4th day, 2/3 by the 10th day, and 90% by the end of 3 weeks. While casualty rates exceeded death rates, they both were highest near ground zero and declined at similar rates by increasing distance from ground zero. But the cumulative death rates in both cities rose dramatically during the first 2 weeks, then leveled off in subsequent weeks.
Dum-dum, beetle-dum-dum, beetle-dum-dum, beetle-dum-dum. There was a turtle by the name of Bert, and Bert the turtle was very alert. When danger threatened him, he never got hurt. He knew just what to do. He ducked and covered, ducked and covered. He did what we all must learn to do. You and you and you and you duck and cover. Be
sure and remember what Bert the Turtle just did, friends, because every one of us must remember to do the same thing. That's what this film is all about. Duck and cover. This is an official civil defense film produced in cooperation with the Federal Civil Defense Administration and in consultation with the Safety Commission of the National Education Association. Produced by Archer Productions, Incorporated. Hey, Bert, come on out and meet all these nice people, please. Oh, all right. We really can't blame you. You see, Bert is a very, very careful fellow. When there's danger, this is the way he keeps from being hurt. Sometimes it even saves his life. That's why these children are practicing to duck and cover just as you do in your school. We all know the atomic bomb is very dangerous. Since it may be used against us, we must get ready for it, just as we are ready for many other dangers that are around us all the time. Fire is a danger. It can burn whole buildings if someone is careless. But we are ready for fires. We have a fine fire department to put out the fire, and you have fire drills in your school so you know what to do. Automobiles can be dangerous, too. They sometimes cause bad accidents, but we are ready. We have safety rules that car drivers and people who are walking must obey. Now, we must be ready for a new danger, the atomic bomb. First, you have to know what happens when an atomic bomb explodes. You will know when it comes. We hope it never comes, but we must get ready. It looks something like this. There is a bright flash, brighter than the sun, brighter than anything you've ever seen. If you were not ready and did not know what to do, it could hurt you in different ways. It could knock you down hard or throw you against a tree or a wall. It is such a big explosion, it can smash in buildings and knock signboards over and break windows all over town. But if you duck and cover like Bert, you will be much safer. You know how...
This definitely works!
...burn you worse than a terrible sunburn, especially where you're not covered. Now, you and I don't have shells to crawl into like Bert the Turtle, so we have to cover up in our own way. First, you duck, and then you cover. And very tightly, you cover the back of your neck and your face. Duck and cover underneath a table or desk or anything else close by. In Betty's school, they are talking about the atomic bomb, too. Betty is asking her teacher, how can we tell when the atomic bomb may explode? And her teacher is explaining that there are two kinds of attack, with warning and without any warning. We think that most of the time we will be warned before the bomb explodes, so there will be time for us to get into our homes, schools, or some other safe place. Our civil defense workers and our men in uniform will do everything they can to warn us before enemy planes can bring a bomb near us. You may be in your schoolyard playing when the signal comes. That signal means to stop whatever you are doing and get to the nearest safe place fast. Always remember, the flash of an atomic bomb can come at any time, no matter where you may be. You might be out playing at home when the warning comes. Then be sure to get into the house fast, where your parents have fixed a safe place for you to go. If you are not close to home when you hear the warning, go to the nearest safe cover. Know where you are to go, or ask an older person to help you. You know the places marked with the S sign? They're safe places to go when you hear the alarm. If there is a warning, you will hear it before the bomb explodes. But sometimes, and this is very, very important, sometimes the bomb might explode without any warning. Then the first thing we would know about it would be the flash. And that means duck and cover fast, wherever you are. There's no time to look around or wait. Be like Bert. When there is a flash, duck and cover, and do it fast. Here are some older boys showing what to do if the flash comes when you are not in the classroom. This is what to do if you should be in a corridor. You duck and cover tight against the wall this way. Remember to keep your face and the back of your neck covered tightly. Try to fall away from windows or doors with glass in them. Then, if the glass breaks and flies through the air, it won't cut you. You might be eating your lunch when the flash comes. Duck and cover under the table. Then, if the explosion makes anything in the room fall down, it can't fall on you. Getting ready means we will all have to be able to take care of ourselves. The bomb might explode when there are no grown-ups near. Paul and Patty know this, and they're always ready to take care of themselves. Here they are on their way to school on a beautiful spring day. But no matter where they go or what they do, they always try to remember what to do if the atom bomb explodes right then. It's a bomb. Duck and cover. Paul and Patty know what to do. Paul covered the back of his head so that he wouldn't be burned, and Patty covered herself with the coat she was carrying. They knew how to duck and cover. They acted right away when the flash came. If they had been at this doorway when the bomb flashed, Paul and Patty would have ducked and covered this way, like this girl. Heavy doorways